to last class हमने क्या देखा कि superconductivity, okay, how it is different from a normal state. Superconductivity is characterized by zero resistivity and Meissner effect, and also we have seen that thermodynamics able to tell something about this phase transition from normal state to superconducting transition. Okay, how some properties, thermodynamic properties, changes when you go from normal state to superconducting state, like free energy decreases. Okay, similarly your entropy decreases because superconductivity is a more ordered state. And then we also seen that specific heat also changes. Okay, so specific heat is discontinuous as a transition temperature. Okay, so now let me talk about something about type 1 and type 2 superconductors. Okay, type 1 and type 2 superconductors. Okay, superconductors. Now, what is type 1 superconductor? We have already discussed this thing. Okay, so type 1 semiconductors are which show complete Meissner effect. Complete Meissner effect means which are perfect diamagnetic in superconducting state. So if I draw the graph for a type 1, okay, say this is minus M magnetization, okay, and this is the H. So if you plot the graph, okay, so if you apply the field below TC or below SC, okay, you got exactly straight line for type 1 superconductor. Okay, this is your SC. So below SC, okay, and of course below TC, okay, if you apply magnetic field, okay, it shows your chi equals to -1, susceptibility equals to, okay, M by H, which equals to M by H equals to -1. And as you increase the temperature beyond SC, it comes to normal state. This is a normal state. Okay, and this is your superconducting state. SC, superconducting state. Okay, so this transition is sudden. When you are in superconducting state, your material is perfect diamagnetic. Okay, and the transition is sudden. Transition is sudden. Okay, but this SC value is very low. In type 1, SC values are low. The critical field values are low. Okay, critical field values are low. Low means they don't have any technological applications. Okay, so say order of say 0.1 millitesla or 0.1 tesla, let's say Gauss, some 100 Gausses. Okay, so they don't have much technological benefits. Okay, so this is a type 1. Type 1. Now type 2 superconductors, okay, they don't show complete Meissner effect. Okay, and they have.
Sir, here critical field means what, sir?
Critical field means the field when you apply, the superconductivity will be destroyed. Okay.
Oh, yes, sir.
Critical field means SC. Okay.
Sir, I have one more doubt. Sir,
Yes.
as we were discussing that critical field means sudden decrease of the temperature, na?
No, critical field is nothing to do with temperature. Okay, temperature is a different thing. I told you superconductivity can be destroyed by 3 ways. Okay, either you change the temperature. Okay, either you vary the temperature. If you go up to TC or beyond TC, you will be normal state. Okay, other ways you apply critical field. Okay, you applying a critical field, and critical field also depends on temperature. At what temperature you are present. Okay, so I told you the graph between critical field also. So if you plot the graph between SC and T, okay, this come like this. This is T equal to TC. Okay, and here you have SC. At T is equal to 0, you have SC naught value. So your SC is function of 1 minus T by Tc square. Okay, so if you apply, if now depends on temperature, what temperature you are. Okay, of course you should be below temperature Tc. Okay, so you can be in any temperature below Tc, and that temperature, what is the Sc? Okay, that much Sc should not apply. Are you getting my point? Okay.
Yes, sir.
Okay, that so Sc also depend on temperature. Okay, agar aap if you are in 0 Kelvin, okay, and if you temperature scale you are in 0 Kelvin, then you have to apply this much Sc. Okay, if you are somewhere here, okay, then you have to apply this much Sc. If you are here, you apply this much. If you are in Tc, then you don't need a Sc. Okay, or automatically superconductivity state is destroyed. Okay, so now, so as you increase the temperature beyond Sc, the temperature can be anything, okay, but it should come out as, it should be the temperature where you can transit from superconducting state to normal state. Okay, that's the point I'm talking here. So now this is a Meissner effect. Okay, there's a complete Meissner effect in the case of type 1 superconductor. Okay, there is a sudden transition. You apply magnetic field, you destroy the superconductivity. Now in the case of type 2, okay, instead of 1 Sc, you have 2 critical fields. Okay, Sc1, okay, and after that your transition is not sudden, it slowly comes out. Okay, slowly magnetic field penetrates, and at the temperature at the magnetic field called Sc2, higher critical field. Okay, so Sc1 is what? Lower critical field, lower critical field, and your Sc2 is upper critical field. So what do you mean by lower and upper? So lower critical field is that field, okay, before that your material is showing perfect diamagnetism. That means here chi is equal to -1. Okay, here also it is a superconducting state. Okay, and here what happens? Here you have slowly magnetic field start penetrating inside the material, but it's not penetrating suddenly. Okay, so the state between Sc1 and Sc2, okay, this state is called your vertex state, or it is called your mixed state. Okay, so this is your, let me draw it first. Okay, so the purpose why I'm drawing like this, it will be clear now. Okay, so this is my
Sir, it
this is-
means, sir,
this is
after Hc1 superconductivity will destroy.
superconductivity will not destroy. Okay,
Yes,
superconductivity means what? It should be perfect diamagnetics. Okay, and the resistivity should be infinite. Okay, zero. Conductivity should be infinite. Okay,
yes, sir.
so now when you are at Sc1, slowly magnetic field will start penetrating in your sample. Okay, but your resistivity is still zero. Okay, your conductivity or resistivity also in this zero, resistivity is still zero, conductivity will be also infinite. I'll tell you why. Okay, so this is a mixed state. Okay, mixed state means now slowly penetrating. Okay, so now Sc values are several, Sc2 value is in several Tesla. Okay, it is in several Teslas. So that is useful for us in technological applications. Okay, so that is the difference between your type 1 and type 2. Type 1 you have sudden transition, okay, and type 2 you have a gradual penetration of magnetic field lines inside your sample. Okay, now even your sample is in mixed state, okay, still your conductivity is infinite. Okay, so let me explain that point. Now first of all, what is your vertex state, or what is the mixed state? Okay, so vertex state. Now vertex state means what? You have this, your sample. Okay, you have sample. Okay, now what will happen when you go beyond Sc1? Okay, there will be small regions, okay, where your field will penetrate. Okay, not everywhere. Okay, not everywhere. So this will be the points where your field will start penetrating. Okay, so for example, this is a circular areas. Okay, so what will happen now? Your flux line will go here. Okay, it will come out, will go here. Okay, and this will penetrate inside, and this will come out. This will come out like this. Okay, so there will be small regions in your sample. Okay, that is called vertex. Like there is a cylinder like geometry where your flux line will penetrate. Okay, this will be small regions where your flux line will penetrate inside the sample. Okay, so these small black regions, what I'm showing here, okay, these small black regions, okay, these black region will be normal state. These will be in normal state. Okay, these small black portions where magnetic field lines are penetrating. तो सैंपल में क्या होगा कि पहले क्या हो रहा था, when you go beyond TC, the magnetic field penetrates throughout the sample. Now it will not penetrate throughout the sample. It will go small places. Okay, like this small regions, the magnetic flux line will penetrate here. Okay, and so those regions jahan pe magnetic field is penetrating the region, these regions are normal regions. Okay, these are in normal regions. Okay, I am showing by dark spots, and this remaining area, it is still in superconducting state. This region is still in superconducting states. Okay, and these are vertices. These are what? Vertices. Vertices.
Sir,
So
Sir, as we know that in superconducting state, magnetic field is not able to penetrate. But here in this case, it is able to penetrate through the small holes, right?
Yes.
So how this means holes are created?
So that's why I'm telling na, it is not the Meissner effect. Okay, here it is a complete Meissner effect. Okay, here it is showing complete Meissner effect. Okay, Meissner region. Here slowly your fields are penetrating. Okay, पहले क्या हो रहा था? पहले it's penetrating suddenly. Now it is penetrating slowly as you increase the critical field. Okay, slowly is the magnetic field distribution is increasing, and once you get to SC2, it will completely penetrate and it will become your normal state. The point is here, what happened in vertex state? So when it is in vertex state, still your resistivity is 0. Why? Okay, so suppose now I'm flowing current inside the sample. So there are the portions where you have a conducting, and there are the portion regions where you are and you have normal regions which is a finite resistivity, but still I'm getting 0 resistivity or zero resistance. Why? Okay, so suppose I have two resistances R and one more resistances R. Okay, R1, R2. Say R2 is 0. Now, or you say okay, so I have a sample, say this is R1, okay, and this is R2. Okay, now R1 is greater than R2. Now suppose I am applying voltage. Okay, so what will be the path of current through R1 or R2?
R2.
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 R2 is R1 is greater than na? So current will shunt through R2. जहाँ पे resistance कम है, current तो वहीं से जाएगा ना? Okay, so in this way you can understand this thing. Okay, current will always shunt through or bypass the region where has a lower conductivity. So current will go here through R2 because R2 is less. Okay, similarly you have dark regions which has a finite resistance, and you have some region, superconducting region, which has a 0 resistance. So current will not go through this one, they will bypass this one. Okay, they will current will always choose the path whereas the resistance is minimum. Okay, that's why there's a distribution of current. So this resistance is too much, so almost all current will pass through. That's why still in vertex state itself, still you get the resistivity 0 or the conductivity infinite. Okay, I hope my point is clear to you. Is clear? So,
Yes,
so,
sir.
so you understand what is the about type 1 and type 2. Okay, now let me give some more differences in type 1 and type 2. Okay, so here we have seen that penetration depth, we have already discussed two characteristics lengths. So shall I erase this one? Shall I erase this one?
Yes, sir.
Now in
Sir,
superconductor, बोलिए.
sir, penetration depth can be start from the middle of the sample, or it will be start from the outer boundaries of
Always from,
both.
of course, from outer boundary. Na penetration will be from penetration start from the top only. Na okay, it will be on the surface only if you angstrom. That's why we say interior is completely zero magnetic field, no penetration. The penetration is only up to the surface, only up to 100 angstrom, 100 up to 500 angstroms. Okay, so
Okay, sir.
so your super electron current is only flowing through the surface. Okay, and that because of that current, this is a diamagnetic behavior. Supercurrent is flowing through a surface, and that is creating a magnetic field which is opposing the external magnetic field. That's why you're getting inside magnetic field 0. Okay, so let me give some more points. Okay, yes. So when you are in superconducting state, okay, so there are two characteristic lengths in superconductor. Okay, characteristic length. Put the adding characteristics lengths in superconductor. Okay, so one you already know, one dimension is London penetration depth. London penetration depth. Okay, and others, the important characteristic length is your coherence length. Okay, coherence length, and already I have denoted this penetration depth by lambda L. Okay, or lambda, and this is represented by this symbol, say E, something like symbol E. Okay, Jai, something like simple symbol Jai. Okay, now what the difference between these two lengths? Okay, so this refers to exponentially okay, decaying magnetic field, exponentially decaying magnetic field. Okay, this we already seen. Okay, and the number 2 is your coherence length. Okay, which is the measure of size of Cooper pair. Okay, Cooper pair. So Cooper pair कितनी लॉन्ग डिस्टेंस तक कोरिलेट रह सकते हैं, कितनी लॉन्ग डिस्टेंस तक उसमें कोहेरेंस है. जितनी लॉन्ग डिस्टेंस तक कूपर प्लेट में आपका कोहेरेंस होगा, उतना ही आपका सुपर कंडक्टिविटी ज्यादा स्पेशल वेरिएशन होगा, ज्यादा देर तक, लंबी देर तक आपका रहेगा. ओके, सो दैट इज मेजर साइज ऑफ कूपर पेयर. ओके, नाउ इन द केस ऑफ टाइप 1, okay, in type 1 superconductor, okay, a quantity, I'm defining quantity called kappa, which is proportional ratio of these two lengths. Okay, lambda L or xi. Okay, so this is the kappa, the ratio of two lengths. Okay, this value kappa is less than 1 by 2, 1 by root 2. Okay, in the case of type 1 superconductor. Okay, let me exactly, this is 1 by 2 or 1 by root 2, just let me check. 1 by root 2. So this is for 1 by root 2 for type 1 superconductor. Okay, that means it is less than 1 by root 2. Okay, that means in the case of type 1, the coherence length, okay, coherence length, okay, is bigger than, is greater than, ये क्वेश्चन एग्जाम में पूछते हैं, greater than your penetration length, penetration depth in type 1, penetration depth. Okay, we'll will come to this, we'll detail, okay, next class. So today just you remember that in type 1 superconductor, the coherence length is greater than your penetration length, okay, while in type 2 superconductor, okay, type 2, in type 2 superconductor,
Sure.
हाँ,
So how will define coherence length?
coherence length I told you, na, this is a measure of your size of Cooper pair, okay. So it is basically defined the wave function, okay, which is the Landau theory order parameter, the extension of psi, okay, psi, so how much distance your psi extends, okay. That we'll discuss tomorrow when you discuss Landau theory, okay. Just you today remember these values, okay. So these ratios are less than 1/√2, and in the case of type 2, your kappa value, okay, is greater than 1/√2, okay. It can be 100, 200. That means your penetration depth, okay, penetration depth is greater, okay, greater than your coherence length in type 2. This is the difference between type 1 and type 2, okay. Coherence length, this is the one thing. And your critical magnetic field in type 2 superconductor, okay, your critical magnetic field, lower critical magnetic field and upper critical field, both are dependent on these two lengths, okay. So if I want to write your lower critical field, okay, so lower critical field okay, SC1, that is given by approximately equal to, that is equal to phi naught, okay, pi upon lambda square, okay, and upper critical field SC2, okay, that is equal to phi naught pi lambda your square of xi, coherence length, okay, where phi naught is quantum of flux, okay, flux quantum, this is a flux quantum, okay, flux quantum, okay, flux quantum, okay, and the value of phi naught is h upon 2e, or sometimes they write is a 2 pi h cut, okay, 2e. How do you write 2 pi h cut is h upon 2 pi, okay, 2 pi cancel, so they write like this also, okay, h upon 2 pi or h upon 2 pi, and the value of this fluxon, okay, I'm writing again here, the value of fluxon is equal to 2 pi h cut 2e or h upon 2e, that is equal to 2.0678 into 10 raised to power minus 15 Tesla meter square, okay, in SI unit, and in CGS unit, okay, your fluxon value is equal to 2 pi h cut c by 2e, and that is equal to 2.067 into 10 raised to power minus 7 Gauss centimeter square, okay. So these are the important relations, okay. Questions are asked based on these formulas also, you should remember these formulas, okay. So this was your type 1, type 2, okay. In type 1 you have a perfect Meissner effect, Okay, in other case you have a field penetrate slowly inside this one. Okay, and this is the difference. SC1, SC2 is very high. There are two critical fields, SC1 and SC2 in the case of type 2, and SC2 value is very high. And then there's a difference. Kappa value is greater than 1/2 for type 2 and less than 1/√2 for type 1 superconductors. Okay, now shall I erase this one? Shall I erase this one?
Yes, sir.
Okay. Now today we'll do some problems also. Okay, let me just discuss one more effect. After that we'll solve previous year problems. Okay, put the heading Josephson effect.
Sir, in this topic, basically we are asked from the topics or concepts or formulas.
Mainly they ask questions from formulas and facts. Okay, because it's difficult to make new problems on this topic. Okay, so if you see your previous year problems, they are mainly based on formulas. Okay, and little bit facts and concept. Okay, so we'll see now. I'll solve some problem, then you'll understand कैसे problem पूछ रहे हैं exam के अंदर.
Okay.
Okay, now what is Josephson effect? Can anyone tell me what is Josephson effect? Anyone? किसी ने तो पढ़ा होगा. So what is Josephson effect? Okay, so suppose I have a superconductor. Okay, I have a superconductor, and when I'm flowing current is passing through this superconductor. Okay, I'm flowing this current, I'm applying some voltage from outside. Okay, and current is flowing, and when I'm measuring the voltage across this one, okay, across this superconductor, so this voltage is showing what? Zero resistance. Okay, the potential difference across the superconductor is zero because the current is flowing due to the Cooper pairs. Even though I'm applying electric field here, I'm applying voltage here or battery here. Okay, and because of this, your Cooper pairs are moving, but because since they are moving, scattering less, they are not colliding. Okay, so when I measure the potential difference across the superconductor, it always gives me zero value. So this is your superconductor. Now,
Sir, can you repeat this statement?
So when you apply, when current flows in superconductor, the
Yes,
potential difference across is zero. Okay,
Oh,
then only resistance zero na. Resistance zero. Resistance zero क्या होता है? I told you the current is finite. In superconductor, current is finite, but voltage is zero. Inside electric field is zero. Outside I'm giving electric field. Outside I'm giving voltage. I am pushing electrons. Okay, but that's what we have seen in a London equation. What London equation says, the J dot is proportional to E. J dot is proportional to E. That means if you give E, the current will change. So initially, if I want to start a current, I need electric field. Okay, but current can flow even though E is zero. If E is zero, then also there a constant current can flow through a superconductor. Okay, that's what London equation. So जैसे कोई suppose कोई frictionless surface है. Okay, suppose there's no friction, so you roll one ball, so that ball will be keep on rolling if there is no frictions. Okay, you are giving only one time force, you're pushing one time ball, and once if the surface is frictionless, that will be keep on moving. Similarly, in superconductor, if you apply electric field once, you give force. If it's a perfect superconductor, the current will be keep on moving without any friction. Okay, that means you will get voltage drop across the superconductor zero. Okay, now suppose I break this superconductor in two parts. Okay, now I am breaking this superconductor, say superconductor 1 and superconductor 2. Okay, now what will happen? Now if I try to flow the current, then what will happen? That is explained by your Josephson effect, okay, or Josephson tunneling. So what is normal turning? Okay, normal turning में क्या होता है? Normal turning में if you have two wires, okay, you have two wires, and if you try to flow the current, okay, so there will be I will be equal to 0 because there is a break. If this gap is very high, gap is large, this gap is large. अगर यहाँ पे वायर टूट जाएगा तो करंट तो फ्लो करेगा ही नहीं, okay. But at nano scales, what happens when this gap is very small, in the order of angstrom, okay, when gap is order of angstrom, okay, order of 10 angstrom, okay, or 1 nanometer, then even though there is a gap, still current can tunnel through one conductor to other conductor, okay. That is called your tunneling current, okay. So this is called your tunneling current, okay, which varies with the size of the tunnel or gap. तो जितना बड़ा गैप होगा उतना करंट कम होगा, एक्सपोनेंशियली डिक्रीज करता है, okay. So you have studied this in your quantum mechanics. Even though the barrier height is high, but there is the finite probability that current can tunnel from the barrier, okay. So this is the this gap is the barrier, okay. But then even though it is a barrier, there is a gap, but still there is a finite probability that current can go from here if this gap is in the order of 10 angstrom. So in material, if it is a small gap, current can tunnel. Similarly, if two superconductors, okay, if there is a small gap, okay, if this gap is in nanometer order or angstrom order, then still Cooper pair can move from here to here, okay. Cooper pair can move here to here. Still, when you measure the voltage across this junction, okay, then still it will show zero voltage when still current is flowing. So that's the Josephson effect. So in other words, instead of this is a vacuum, this is air. Instead of this one, if I put an insulator, that is same thing, okay. If I put an insulator, so this is called your Josephson junction. So in Josephson junction, you have two superconductor separated by the superconductor 1, superconductor 2, both can be similar also, okay. They are separated by a layer, insulating layer, okay, insulating layer, okay, whose depth, whose length is less than 10 angstrom, and still, and this geometry is called Josephson junction. Josephson junction, okay. Now Josephson effect, okay. What is Josephson effect? So Josephson effect are two types. Josephson effect, okay. There are two types, okay. One is called DC Josephson effect, and other is called your AC Josephson effect. Okay. Now what your DC Josephson effect says, okay. So DC Josephson effect, can I erase this one?
Yes, sir.
Okay. So what DC Josephson effect says? So DC Josephson effect, okay. Okay. So DC Josephson effect, okay. This effect means a AC current, a DC current, okay, a DC current flows across, okay, the junction, across the junction in the absence of any magnetic or electric field, okay. So even though if you do not apply any field across the junction, then also current can flow in the absence of electric field. When there is no potential difference or no voltage, then also current can flow across the junction. This is called DC Josephson effect. Okay. Now other is your AC Josephson effect. Okay. So AC Josephson effect says when you apply voltage across a Josephson junction, okay, when a DC voltage is applied across the junction means here Josephson junction, okay, the junction, it causes okay RF current oscillation okay, it causes RF current oscillation across the junction, okay. I hope the two definition is clear to you. Okay, so this effect is talking about the junction. Okay, if a superconductor, if two layers of superconductor are separated by a thin layer of insulator, and if you are applying a voltage across this junction, then a AC current will flow of radio frequency through this junction. Okay, and even though if there is no voltage, you apply some voltage and leave it like a ring, superconductor ring, still current can flow, a constant current can flow across this junction in the absence of magnetic field or electric field. This is called your DC Josephson effect. Okay, now let us prove this one. So can I erase this one? I hope
Sir,
this one. बोलिए.
the DC में absence of magnetic or
Electric field.
electric field के मतलब it is presence absence of magnetic or electric field.
Yes.
And the current is being flowed,
Yes.
right?
Yes. That means there's a if current is flowing, then
Yes,
also
sir.
junction can be maintained on the potential difference 0. Okay.
And
zero, but still current can flow. Okay.
and sir, in AC, sir, what you have written, sir, when a DC voltage.
In AC, when you're applying the DC voltage across a junction, okay.
Yes, sir.
So through junction, the current which flow, that will be AC current. That will be radio frequency current. Okay. So that means it is converting. It is a converter. Okay. Like
So how it is converted?
so we are proving that one. Na? Okay.
Okay, sir. Okay, sir.
Okay. So this is your junction. Josephson junction is what? It can convert voltage to frequency. You're applying DC voltage, you are getting frequency. It can go do invert Josephson effect also. You apply frequency, some microwave region frequency, it can give you voltage also. That is called invert Josephson effect. Okay. So let us prove this one. Now suppose I have two superconductors. Okay. Okay, which are okay, superconductor 1, superconductor 2. Okay, so they are separated by this layer of insulator. Okay, layer of insulator. Now if this insulator layer is too big, okay, then I can understand these superconductors are isolated. Okay, they don't have any effect. There is no coupling of the wave functions of electrons. Okay, if this region is thin, then only there is a coupling. Okay, so what I can write, if barrier is thick enough, okay, if barrier is thick enough, okay, in that case what happened, if the barrier is thick enough, then superconductor are isolated. Okay, isolated, that means there is no coupling. So I can write the Schrodinger equation for region 1, say del psi 1 upon del t, okay, equal to what? क्या लिखूं मैं इसमें? Say my energy is E1 or say H1 psi. Okay, E1 psi or H2 psi, whatever you want to write. Okay, and for region 2, for region 1, okay, region 1, this is my region 1, and region 2, I can write iota h cross del psi upon del t. Okay, s2 psi. Okay, because both these are isolated. There is no relation, no coupling, because the thickness is very large. So you can independently write Schrodinger equations. Okay, but if there is a coupling, okay, if barrier thickness, if barrier thickness is small, okay, in that case these solution will not be independent. Okay, in that case I can write iota h cross del psi 1 upon del t equal to, suppose I am applying a voltage. Okay, I am applying a voltage across this junction. So the difference between the energy levels of two junction, two parts, psi 1 psi 2 will be what? QV. If I am applying voltage, if there is charge, so the separation difference will be QV. Now here instead of QV we have a super electron Cooper pairs. So instead of having EV, the difference when I apply voltage difference here, and the voltage difference between these two superconductor, instead of having EV, that then in energy, okay, if I am applying a voltage difference here, okay, if I am applying a voltage difference V here, so energy difference will be EV, but now here electron pairs are there. So instead of EV, the energy difference between two contacts here, two superconductor, will be 2 EV. Okay, so one side you will be having EV, okay, psi 1, and then will be K psi 2. K is a coupling constant. What is the coupling between these two layers? Similarly, if I write iota h cross del psi 2 del t, okay, this will be minus EV, difference is 2 EV, okay, psi 2, okay, plus K psi 1, okay, where K is what? K is your coupling constant, coupling which is coupling to wave function, and psi 1 is what? Sine is the wave function of electron. Okay, wave function, psi 1 psi 2s are wave functions of electrons, super electrons. Okay, so if I take the magnitude of psi square, it should give me what? It should give me super electron probability density. If I take the mod of psi square, the mod of psi square is equal to the probability density. So I can write my function psi 1 is equal to n power half n1 power half e power iota theta 1, and I can write psi 2 equal to n2 power half exponential I power theta 2. These are my wave function. If I take the amplitude square, that will give me what? The density of superconducting electrons. Okay, n1 and n2. If I square it 1, this will give me n1, probability n1, and this will give me the electron. Here you have density of superelectron as n1. Here you have density of superelectron n2. Okay, if you're taking similar, then n1 can be equal to n2. Okay, now you have the equations and you have the wave function. Okay, put this wave function in this equation and separate real and imaginary parts, so that you will get the solutions. Okay, do it. Put the values here. Okay, put these values here and give me the solution. So I have psi 1. Okay, I want del psi 1 upon del t. Okay, so differentiate this equation. Okay, say this is your equation 1a, this is equation 1b. Okay,
Sir, here N1 represent what, sir?
super electron density.
Oh.
Super electron density. Okay, N1 N2 are super electron densities in two regions. Okay, now I have psi 1. Okay, so del psi 1 upon del t. Differentiate this equation. So if you differentiate this equation, this will give me root n. Okay, root n. and this is n1 and dn1 upon dt. Okay, exponential will be as it is, and next time if I differentiate, my n1 power half will be as it is. Okay, and I have to differentiate exponential. So if I differentiate exponential, it will give me iota exponential iota theta 1. Okay, so exponential iota theta 1. Okay, and when I do theta 1, it will give me the d theta 1 dt. Okay, similarly you can differentiate this equation. Okay, now put this value in this equation and solve for solution. Okay, so now if I solve this one, if I put this value here, okay, so let it take e power iota theta 1 common. So this will be what? Half under root n1 dn1 dt plus iota n1 half d theta 1 by dt. Okay, now plug this value in this equation. So if you plug this value here, iota h cross del psi upon del t, it will become iota h cross e power iota theta 1 1 upon 2 1 upon under root n dn1 by dt plus iota n1 power half d theta 1 by dt. Okay, and that will be equal to what? That will be equal to ev ev psi 1 is what? n power half e power iota theta 1. Okay, and then if you put k here, you have to multiply. Okay, yes, and k, your psi 2 is what? Psi 2 is n2 power half e power iota theta 2. Okay, अब आगे solve करो. Now solve this one and separate out real and imaginary parts. So if I solve this one, okay, shall I erase this one, this part? Okay, now if you further solve, okay, divide this equation, divide by iota h cross e power iota theta 1. So if you divide this equation, what you get? You'll get half under root n. Okay, and you divide this equation better by iota h cross iota theta 1 and n power minus half. Okay, you divide by this equation. So what will get? You'll get half. This is cancel. This n power half cancel. So you'll get dn1 upon dt. Okay, plus here this is cancel. Okay, this part is cancel. n1 go here. Okay, so this will give you iota n1 d theta 1 upon dt. Okay, आप भी सॉल्व करो. Okay, कितना आ रहा है चेक करो. So if I solve this one, okay, what I'm getting, half dn upon dt iota n1 d theta 1 dt, okay, equal to here I have ev n1 power half, okay, and n2 power half. So I'm dividing by n1 power minus half. Okay, so this will become n1. So what I'll get? I'll get k. Okay, e, this is e ev. Okay, n1 n1 ev n1 and okay by h cut iota h cut. Okay, iota h cut plus I'm directly writing. Please solve it. Okay, so ev n1 I theta and k. Okay, k upon iota h cross. Okay, n1 n2 power half. Okay, e power iota theta 2 minus theta 1. If you solve this one, you'll get this equation. But आसान है, that is not कोई complicated mathematics नहीं है. Just write, just differentiate and now separate out. Now यहाँ पर ये real part है, ये imaginary part है. Okay. Now यहाँ पे if you open this one as cos theta plus iota sin theta, you can separate out this real and imaginary part. Okay. So what you have to do, just write this is a real part, dn1 upon dt plus iota n1 d theta 1 upon dt, okay, equal to ev n1 iota h cross, okay, plus k upon iota h cross n1 n2 power half, okay. I'm erasing this one, okay, and this you open, say theta 2 minus theta 1, say it is del, okay. So this will be what, your cos del plus, okay, cos del plus iota sin del. I hope you are understanding this mathematics. I can directly write the results, but it is better to you do at least one time.
Yes, sir.
Okay. Okay. So now this is the equation. Now you can separate it out. The real and imaginary part, I'm directly writing what I'll get. So if you separate real and imaginary parts, okay, what you'll get, I'll get h cross dn1 by dt 2 k n1 n2 half sine delta, okay. This is my equation, say third A, okay. Similarly, for you solve for theta, you'll get the equation d theta 1 upon dt equal to minus ev upon h cut n1 minus k n1 k upon h cut, okay, n2 upon n1 power half cos delta is 3b. You'll get this one. So इसमें हमने क्या किया, I have taken psi 1 and I use psi 1 in the first equation. Similarly, you can take psi 2, differentiate, and you can make 2 more equations. Okay. So this equations, हाँ बोलिए.
What is the third B equation, d psi 1?
D theta 1 upon dt. Theta 1. Okay.
Okay, sir.
EV upon h cut n1 minus k upon h cut n2 upon n1 half cos delta. Okay. Similarly, if I solve for psi 2, okay, so I'll get the same kind of equation. Okay, h cut d n2 upon dt minus 2k n1. You can do it yourself. Okay, so sine, mathematics is not important, results are important. Okay, but you at least one time you have to do. We should do. Okay, so this will give me e v upon h cut minus k upon h cut, okay, n1 upon n2 power half cos del. Okay, say this is equation third b or 4b, 4a, and say this equation is 4b. Okay, so these are the equations. Okay, now what we can do, now I want current, I want the expression for current density. Okay, I have to see what's happening when I'm applying, if I'm applying voltage across the junction, what is happening. So that I have to check. So obviously I need the expression for current density. So are you people getting same expression now?
Yes, sir.
Okay. So now we have the expression. Now just write the expression for current density. Okay. So if I want current, okay, current density J, current is nothing. Current is basically your E d upon dt n1 minus n2. Okay. So you have to equation 3rd A and 4B. You can put the value of dn1 by dt and dn2 by dt in this equation, and you will get the expression for current, and that will come out as a 4ke, okay, upon h cut n1 n2 power half sine del. Okay, what is the meaning of this one? So the meaning of this one is, shall I erase this one?
Yes, sir.
Yes, sir.
So if you divide this one, you'll get J equal to JC, okay, JC sine delta. Okay, this is the equation number 1, equation number A for Josephson junction, Josephson effect, equation number A. Okay, similarly, if you calculate d theta 2 minus d theta 2 minus theta 1 dt, that is del phase difference, okay, between the two things, d del by dt, okay, that will come out as 2 ev upon h cut. Okay, so these two are the final conclusion for your Josephson junction. Okay,
So please explain third line. J is equal to E d by dt and 1.
this one, e d by dt n1 minus n2 equal to 4 ke upon h cut n1 n2 power half sine delta. Okay, this is the current density. And similarly, if you multiply by the area, you can write I equal to IC sine delta. Okay, and del delta upon del t equals to 2v upon h cut. Okay, current, rate of change of charge, this is nothing here, current. Okay, if you multiply by this one area, it becomes current density. Divided by area, current density, multiply by current, it will become you multiply GC by A, it will become current. Okay, हाँ बोलिए क्या बोल रहे हैं
सर? J equal to rho into V होता है ना, चार्ज डेंसिटी into velocity.
J equal to सिग्मा ई होता है,
any V.
हाँ, J equal to any V होता है. ओके,
हाँ तो सर,
तो ये J equal to क्या होता है? J equal to I by A भी होता है. ओके, I क्या होता है? 1 by A. I क्या होता है? dq upon dt होता है. ओके, now this is what? This is charge densities ना? Okay, so this is charge densities. So this forms current. Multiply by charge forms current. Okay, current per unit area. Now multiply you by area, you will get current. Okay. So now finally we can conclude what we have got. We have these two equations.
The last two line.
हाँ, उसी को लास्ट टू लाइन ही इंपॉर्टेंट है. आपको डेरिवेशन इतना इंपॉर्टेंट नहीं है, बट मैंने कर दिया क्योंकि लाइफ टाइम में एक बार तो करना ही चाहिए. So this is your equation. Now these equation will explain us what is your DC Josephson effect and AC Josephson effect. Okay, so if I put V equals to 0, if I put V equals to 0 here, then my phase is constant. Say if V is equal to, say phase is what? Phase is equal to delta 0. And my current will be what? My current will be I equal to IC sine delta 0. So even in the absence of voltage, a constant current can flow through, this current can flow through your junction. Okay, and this is called your DC Josephson effect. DC Josephson effect. Okay, and if you apply voltage, okay, if you apply voltage, then if V equals to V0, you are applying some voltage V0, okay, then you have del T is equal to 2 EV0 upon h cut So delta will be what? Delta will be simply 2e v naught t upon h cut plus you can put some delta 0. Okay, so your current will be what? Current will be I equal to IC sine delta value is what? 2e v naught t upon h cut plus del 0. So this is nothing, this is the AC current. So a time varying current or a RF current will be generated across this junction. So this is your AC Josephson effect. It's your AC Josephson effect. If there is a no voltage, this is Josephson effect. If there is a voltage, then this is the AC Josephson effect. Okay. And there is an inverse Josephson effect also. Inverse Josephson effect. So this equation can be written what? This equation can be written as I equals to IC sine omega t plus delta naught, where the frequency of this AC wave is 2e v naught upon h cut. Okay. This is the frequency of oscillation, and this frequency in the range of microwave region or radio frequency regions. Okay. So this is the AC Josephson effect. And now what is inverse Josephson effect? In inverse Josephson effect, if you give some radiation of microwave frequency, okay, if you give frequency, so this is what? This is your voltage to frequency converter. Voltage to frequency converter. And inverse Josephson effect, what happens when you apply some frequency to junction, you give some light, microwave light. If you give microwave frequency radiation to junction, okay, then quantized voltage will develop. Okay, then quantized voltage will develop across the junction. Quantized voltage will develop across junction. That is called inverse Josephson effect. Okay. Now let us give 5-minute breaks. Okay. ये बहुत derivation हो गया है. Now after 5 minutes we'll meet again, and then we'll solve.
Inverse वाले में what you have told, sir?
Inverse में if you have a micro frequency radiation and you radiate the junction with this any frequency radiation, then across the junction you will get what? You will get voltage. Okay, आप voltage लगा रहे हो तो क्या आपको AC frequency मिल रही है? Frequency मिल रही है क्या?
So it is used in MRI.
Yes. I didn't get the question. What are you saying?
So this phenomena used in MRI.
Yes. Okay, so there are many applications of Josephson effect. Okay, we'll discuss tomorrow this one. Okay, so this was your Josephson effect. We'll meet after 5 minutes to solve some problems. Okay, please give us break. Okay, now we'll solve some problems. बहुत आसान problem आती है. Okay, the problems are very easy from this part of the syllabus. Okay. So I hope all are there. Okay, so one question is asked in CSIR net June 2021. Okay, so in this, what they have given, okay, so this is some port, okay, which is filled with liquid, okay, and this is filled with some mercury, okay. Now what they're doing, they are putting two wire inside this chamber, okay. So these are two niobium wires, okay, niobium titanium wire. Niobium titanium is an alloy which can become superconducting, okay, and this is the mercury. Now what they're doing, they are cooling this mercury up to 10 Kelvin, okay, and they are measuring the voltage across these wires, okay, and they say the resistance of wire is R and they are flowing current I, okay. So they say what will be the voltage, suppose this height is H and the length of the wire is given N. Length of the wire is L, okay. So this total length of the wire, this wire length, total length is L is given. So this height will be what? L by 2, isn't it? You have a wire is given, the full length is L. So this is half part of length. So this the total length of this vessel is what? L by 2. Okay.
L by 2.
Yes. Okay. Now they are giving options. What is the correct expression for the voltage? A, IR 1/2 minus 2H upon L. B, IR 1 minus H upon L. C, IR 1/2 minus H upon L. D, IR 1 minus 2H upon L. Okay, which is the correct option? What is the V? They are asking what is voltage across this wire. Resistance is L. So we know whenever you measure the voltage should come V equal to IR if it is in normal state. Okay, but here it is not in normal state. Some portion of the wire is filled with this liquid, isn't it? So the portion of wire which is inside this mercury, and mercury is cooled up to 10 Kelvin, so that portion becomes superconducting. So that portion will give zero resistance. So you will not get V equal to IR. V equal to IR only you'll get when there is no mercury inside. Okay, if it is mercury inside, this is cooling this superconductor, so this portion will become zero. Okay, so out of the which expression is correct expression? Okay, so if you put H is equal to 0, if there is no mercury, okay, if H is equal to 0, then you should get V equal to IR, isn't it? If there is no mercury, no cooling, then it is a normal conductor, and if you measure the resistance, it should come voltage, it should come IR, because you are flowing the current I and resistance already given is R, so it should come V equal to IR. Okay, so if you put F equal to 0, this expression should give you V equal to IR. Now you put H equal to 0 here, this is IR. H is equal to 0, IR. H is equal to IR. H is equal to IR. So all the options are correct. Okay. Now if I put L equals to L by 2 equals to H, H equals to L by 2, if this H is completely filled up to L by 2 height, then this whole wire, what will become? That wire will become superconducting, and then voltage across the wire should come 0. So which option is giving 0 if H is equal to L by 2? If H is equal to 0, if H is equal to 0, you should get V equal to IR. So all the options are giving. Now if H is equal to L by 2, only D option will give you V equals to 0. So option D is correct. I hope the question is clear. किसी का आवाज ही नहीं आ रहा है.
Yes, sir.
Please repeat again, please.
Which portion I should repeat?
Last line. If H is equal to L by 2.
If H is equal to L by 2, that means if this full vessel is filled up to here, if it totally filled here, this whole wire will become superconducting. When wire becomes superconducting, there will be no potential. There should be no potential difference because this resistance is 0, conductivity is infinite. So which option is giving V equal to 0 for H is equal to L by 2? Only D option, because you put L by 2 here, you won't get 0. Clear?
Yes, sir.
Okay.
Sir, means only superconducting state arises in H region.
H regions, yes. जहाँ पे कूलिंग होगी वहीं भी तो भी यहाँ पे जहाँ पे कूलिंग होगी वही तो पोर्शन सुपरकंडक्टिव टाइप फेज जाएगा.
Yes.
Yes. Any other question?
So the expression H is equals to 0.
If H is equal to 0, that means no cooling is there. Then it is become ordinary wire, not superconducting wire. Ordinary wire में resistance क्या होता है? V is equal to IR.
IR.
Okay. So if you put H equal to 0, so all expressions is giving IR. So that is correct. Okay. But only this option is giving 0 for H is equal to L by 2. Okay. Clear?
Yes, sir.
Okay. So that's just they will test your knowledge. Okay, just they will check your formula in this subject, in this syllabus. Questions are very simple. Okay, so let us do one more problem. Okay, it is a very simple question. A true test of superconductivity. A true test of superconductivity developing in material is, okay, number A, only when resistance is equal to 0. B, magnetic susceptibility X is equal to -1. C, magnetic susceptibility chi equal to 1. And D, only when conductivity becomes very high. Which option is correct?
B.
Option B.
Option B, na? Option B. Okay.
B.
Option B is correct. The true test is paramagnetism, perfect paramagnetism. Okay. Any question? Okay. This was easy question. I'm erasing this one. So one more question is, a critical magnetic field of superconductor at temperature. Okay. Critical magnetic fields are given. Critical magnetic fields. Okay. They given. Okay. at temperature 4K and at 8K. Okay, so say SC1 is given 11 milliampere per meter. Ampere per meter means this is a Weber per meter square, means B should be B. Ampere per meter or milliampere per meter is your SC1. Okay, magnetic field SC1 is given at 4 Kelvin. Okay, so T1 is your 4 Kelvin, and for this for any given material, okay, because SC varies with temperature, so it says at T equal to 4 Kelvin, SC1 is 11, and T2 equal to 8 Kelvin, they are given SC2 equal to 5.5 milliampere per meter. Okay, so asking what is the transition temperature, what is TC? We're asking TC, calculate TC. How to calculate?
Sir, HC equal to HC0 into 1 minus T square by TC square में ratio करेंगे.
Calculate करो. So what is the formula we have to use? Formula we have to use SC equal to SC0 1 minus T square upon TC square, or TC square upon T square.
T square by TC square.
Okay, T square by TC square. This formula you have to use, and you have to find out what is TC. Okay, so you have SC1 is 11. Okay, 11 equal to SC0. Okay, 1 minus T1 square. Okay, SC1 is equal to T1 square TC square, and SC2 is equal to SC0 1 minus T2 square TC square. Okay, now take ratio of SC1 by SC2. Okay, this will give you 1 minus T1 square upon TC square. Okay, 1 minus T2 square upon TC square. Okay, so SC1 by SC is equal to 2. Okay, 1 minus T1 square is how much given? 4 Kelvin. This becomes 16 TC square, or let me T1 square now. T1 square TC square. Okay, and you have here 2 into 1 minus T2 square TC square. Okay, so 2 minus 2 T2 square TC square, or take TC square common. Okay, so if you take TC square common, this becomes 2 TC square minus T2 square. Okay, and TC square minus T1 square. Okay, so 2 TC, so 2 TC square minus TC square. Okay, and here you can write 2 T2 square minus T1 square. So TC square equal to 2 T2 square. T2 is given how much? 16, 8, 64 minus 4, 16. Okay, so this become 128 minus 16. This give you what? 1112 Kelvin TC square. So TC should be how much?
10.5.
10.5. Okay, 10 should be 10 point. How much is given? 10.58. Yes, 10.58. Okay, Kelvin. This is the correct answer. Okay. Now this TC is not constant. Okay, your TC is not constant for given material. Okay, suppose I have given a lead. Okay, for lead I have given some TC value. So TC value also varies with isotope. Okay, that is called isotope effect. Isotope effect. Okay, for given element, for a given element, okay, TC, okay, is inversely proportional to its isotopic mass. Okay, that is your M alpha TC equals to constant. So if you are given many isotopes, so this result comes from BCS theory, that the transition temperature for those isotopes which are heavier, they will have a lesser TC, okay, compared to the lighter one isotopes. Okay, so generally alpha value is equal to 0.5. So you also write this as a TC equals to under root M. Okay, M is the isotope mass, atomic mass, or atomic or molecular mass. Okay, isotope mass, atomic mass, atomic or whatever given, atomic isotope mass. Okay. This fact is clear, or should I explain again? This point is clear?
Sir, sir, once more.
So I'm telling the transition temperature for a given material can have many isotopes. Okay, carbon can have many isotopes. Any nitrogen can have any element can have many isotopes. Okay,
Yes, sir.
so the transition temperature depends on the mass of isotope. Okay, like M alpha, and generally is alpha value is 0.5. This will be given in the question. Generally, if it is not given, you can take alpha equal to 0.5. Okay, clear? So let us do one problem based on this formula. Shall I read this one?
Yes, sir.
This is isotope effect. So the question is given. So they're saying that transition temperature of a BCS superconductor. Okay, BCS superconductor. BCS superconductor means which follow the BCS theory, and BCS theory is followed by type 1 superconductor. So basically talking about type 1 superconductor. Okay, with an average atomic mass of 190. Okay, so that the TC is given. TC is given as 4.18 Kelvin. Okay, for atomic mass M1 199.5 atomic units. Okay, his mass is given. So you're asking what will be the transition temperature TC2 for a isotope. Okay, for a isotope. Okay, say M2 is given 0.3.4 atomic mass unit. Okay, so calculate what is. Two isotopes are given which have a slightly variation in the mass. One has a TC, this one, other you have to calculate. Calculate and tell me.
So
Yes.
here we will use direct formula, no? TC direct 1 upon under root M.
Yes. So what I'm getting, you are getting TC equal to 4.14 I'm getting. Okay, 1.4413. Okay.
139 आ रहा है.
Yes, sir.
Okay.
4.14.
Okay. ठीक.
So then what is the use of this TC1, sir?
So you use the formula, na?
तो वो तो डायरेक्ट 1 upon under root M2 से निकल जाए.
प्रोपोर्शनल है ना, इक्वल थोड़ी है.
Oh, okay, sir.
ओके अल्फा कैसे निकालोगे तुम? और तो कुछ तुमको बताया नहीं ना इसमें, खाली ये बताया, वो तो बताया नहीं है। ओके इक्वल नहीं, प्रोपोर्शनल है। So now one more important questions I'm giving, which came in net. Okay, CSIR net. Okay, so this question is a flux quantum. What I told you, phi naught. Okay, is equal to 2 into 10 raised to power minus 7 Gauss centimeter square. Okay. Now a type 2 superconductor is placed in a small magnetic field, which is slowly increases till the field start penetrating the superconductor. The strength of the field at this point is given. Okay, so he's saying a type 2 superconductor is there. Okay, and we know in type 2 superconductor we have two critical magnetic field, SC1 and SC2. Okay, so he says that he is given the value of SC1. He says at this SC1 field start penetrating, and the value is given 2 upon pi into 10 raised to power 5 Gauss. Okay, okay, so you're asking what is the penetration length, question 1. Okay, and in second question you're asking, okay, if we go further up to SC2, okay, the magnetic flux completely vanishes. Okay, and this happens at SC2 equals to 8 upon pi into 10 raised to power 5 Gauss. Okay, then you're asking what is the value of coherence length. Okay, so that is the value of xi. I hope my question is clear to everyone. It is given, they are giving you type 2 superconductor. Okay, and they have given you the values SC1, SC2. SC1 is the value where field start penetrating, and SC is to the value where field completely penetrates. Two values are given you. Okay, you have a type 2 superconductor. Okay, so up to SC1 there is no penetration of magnetic field. Okay, after SC1 it start penetrating, and up to SC2 there is a complete penetration. That means become normal.
So this is type 1, no, sir.
Where is type 1? Two critical field is given in what one in the case of type 2, not in type 1. Okay, so this is a lower critical field.
So then vertex state is what, type 1?
This is the curve shown by this. Okay, is the characteristic of type 2. टाइप 1 में तो टाइप 1 में इतना होता है. टाइप 2 में क्या होता है कि यहाँ तक तो SC1 तक तो वो कंप्लीटली सुपरकंडक्टर होता है, कंप्लीटली पैरामैग्नेटिज्म होता है, and complete marginal effect, and then slowly field penetrates, and here field completely penetrated inside the superconductor. Okay, so they are given you critical field values SC1 and SC2, and they're asking what is lambda L and lambda 2, lambda L and coherence length. What is the formula?
So lambda is 10 to the power minus 6.
Phi naught by
Very
pi
good.
lambda.
Okay, so your SC1 is what? Approximately equal to, no, it's not completely equal to, it's approximately equal to phi naught pi lambda L square, and SC2 is your phi naught pi e square. Okay, tell me the values of lambda L. What is lambda L is coming?
10 to the power minus 6 centimeter.
And what is
10 to the power minus 6.
Okay, this is what is E value. Okay, so if you put the values, okay, you put the values in this formula, phi naught value already I have given you. Okay, S1 has been given you. So if you pull this value, you will get lambda L equal to 10 raised to power minus 6 centimeter. Na?
Yes, sir.
So if you put in angstrom, you multiply by 2 and divide by 2, to 10 raised to power minus 8 centimeter. So this will become you what? It will become you 100 angstrom. Okay, answer is given in angstrom, 100 angstrom. Similarly, what will be the value of this one?
0.5 into 10 power minus 6
5 into 10 to the power minus 7 centimeter.
Or 0.5
5 into 10 to the power minus 6
7 6 or 7 है
सर 6 minus 6 सेंटीमीटर अभी होगा
-6 है ना. अच्छा
6
ओके. सो ये 5 करेंगे तो क्या हो जाएगा 10 to the power -7 हो जाएगा. अगर 50 करेंगे तो क्या हो जाएगा 10 to the power -8 हो जाएगा. ओके. सो दिस विल बी व्हाट 50 एंगस्ट्रॉम. सो आई टोल्ड यू टाइप 2 में क्या होता है. टाइप 2 में ये कम होता है. इन टाइप 2 your lambda upon E naughts are greater than 1/√2. So penetration depths are high. That's why it's coming 100 angstrom, and this is coming your 50 angstrom coherence length. And even though these lengths are very small, 100 angstrom is nothing. Okay, if you have a sample of thickness say 1 mm, 2 mm, angstrom is nothing. That means your field is only penetrating surface. Inside it is completely field is zero. Superconductor. Okay. Yesterday some students are asking, so how electric field is when zero, how current is flowing. Okay, someone I know some students are asking. Okay, so that's what we have seen in London equation. Okay, that J dot is proportional to E. Okay, you have to inside is different thing. Outside you can give field na at least, because superconductor है उसके बाहर से तो you can apply force na. And what happens that is a different thing. When you take the perfect conductor में क्या होता है. In perfect conductor also E is zero. When you have studied your electromagnetic theory, and if you make any Gaussian surface inside your metal, there is no charge, because in metal all the charges are on the surface. So if you take a Gaussian surface, inside there is no charge. So the electric field inside the your metal is perfect metal is also zero. Okay, but that is in a stationary state. Your metal is there, you're applying outside electric field, it's stationary state. Okay, if you're applying voltage, if you're applying voltage continuous battery, then there will be no zero electric field. Then there will be electric field and current will flow. It will try to shield outside electric field, but when you are applying continuous battery, that time field is not zero. Okay, field is zero only electrostatic case. If you are applying your metal and you are applying electrostatic force, so that metal will get polarized. Polarized means all the charges will be on surface. So inside, if you plot any Gaussian surface, there will be zero charge. So the electric field is zero. But it's not a true when you continuously applying battery, then you continuously pulling electric. That's why your current is flowing. Na? If electric field is zero, metal the current will not flow. But that is superconductor. It is different thing. In superconductor, you don't need voltage current to flow, but you have to give start. That is J dot is proportional to E. In order to change the current, you need to apply field. Okay, you have to apply some battery. So J dot means initially zero, you apply voltage, some current will flow, and then you remove the battery. Okay, still current will be flowing if it is a ring. Okay, if it is ring, that still current will be flowing. That is the difference between a superconductor and a perfect conductor. I hope it is clear to you.
सर ये जो करंट है ये vortex region में जो करंट है वो सेम करंट HC1 के पहले जो करंट था वो सेम है.
करंट तो भी आपका रेजिस्टिविटी जीरो है. भी हम जो वोल्टेज मेजर कर रहे हैं, ओके, दैट वोल्टेज इज जीरो. दैट अदर थिंग आई डोंट नो. ओके, because current will shunt through ना. जहां पे भी लो रेजिस्टेंस होगा, current will go through low resistance path. Okay, so even though there is a vertex regions, okay, there are vertex regions, these are normal, they have finite resistance, but current will not pass through. That will simply choose a path where we have low resistance. Okay, so voltage
सर बट सर मेरा ये कि करंट सेम होगा.
वो कैसे पता?
पहले जो करंट
वो कैसे पता? वो अगर वोल्टेज जीरो है तो वो उसके ऊपर हम कुछ कह नहीं सकते. फाइनाइट करंट होगा, बस फाइनाइट करंट होगा.
सर ये जो एक्सप्रेशन है ना HC1 का, उसमें फाई नॉट है, HC2 में भी फाई नॉट है.
फाई नॉट तो करंट पे कैसे डिपेंड करता है? फ्लक्स
नहीं, अगर वो जो एम्पियर्स लॉ है, एम्पियर्स लॉ के साथ अगर कंपेयर करेंगे,
हाँ, पर यहाँ पे फाई नहीं है, ये फ्लक्सॉन है, एक कांस्टेंट वैल्यू है ना, तो यहाँ से आपको फाइनोट तो कांस्टेंट ही मिल रहा है ना, ठीक है।
हाँ सर,
पर यहाँ से तुम
वो तो एक डायमेंशन ऑफ करंट है, मतलब अगर एम्पियर्स लॉ के साथ कंपेयर करेंगे, H dot क्लोज लाइन इंटीग्रेशन H dot dl इज इक्वल टू आई एन क्लोज, तो ऊपर इक्वेशन में H इंटू पाई लैम्डा स्क्वायर और नीचे इक्वेशन में H इंटू पाई जाई स्क्वायर।
इसके बारे में तो करंट के बारे में यहाँ से हम स्टेटमेंट कैसे दे सकते हैं भी, हमारा चलो SC1 हमारा फिक्स है ना, सपोज हमारा अवर SC1 इज फिक्स, ओके, SC2 आल्सो फिक्स, SC1 फिक्स इज दैट मींस आवर पेनिट्रेशन डेप्थ दिस इज फिक्स, here it is also fixed, okay. So I don't think we can interpret anything like current, okay, or maybe current may be also same, okay, but I don't have idea. Let it be think, okay, let me think and give you reply tomorrow, okay, because I'm applying some battery, okay, and current is flowing, okay, the current must change, current must change, okay, still because the materials are different now, okay. Let me think and tell you, okay. Any other question? Any other question?
Okay, sir. Thank you, sir.
Okay.
Good night, sir.
So I'm stopping here, okay. Thank you very much.
Thank you, sir.
Thank you, sir.